Hi, everybody. This is just a brief additional note about the Zoom session for Lecture 9 of Electrical Engineering 331. In the Zoom session for this lecture, we evaluated convolution integrals in our discussions of problems 2 and 3 on Test 9. In our discussions of both of these problems, we had an integral that looked like this, where in each case f of t was related to f of tau was related to x of tau and h of t minus tau. But I'm not too interested in that part of the integrand right now. What I'm interested in is u of tau and u of t minus tau, and our discussions of how these terms in the integrand could be handled, and the integral could be more simply written like this: is the integral from 0 to t of f of tau d tau times u of t. And if you will review the recording of the Zoom session for Lecture 9, you will see that what we did in each case was that we first considered the u of tau term in the integrand. And that was real easy. That just led us to replace the lower limit of the integral. That lower limit of negative infinity was replaced by 0. And then we had a somewhat more involved discussion of the u of t minus tau term. And we that discussion led to the replacement of the upper limit of positive infinity by t, and also the introduction of the u of t term outside the integral. And so it just occurred to me that you might be interested in seeing the procedure of handling those in the reverse order. Well, obviously we get the same result, but it's a slightly different way to think about it. And so I encourage you now to stop this video and to try to think about it first, how it would go if you first eliminated the u of t minus tau term and then eliminated the u of tau term second. And you might like that way of thinking about it better. So stop the video for a moment, think about it, think about how it would go, and then come back and I'll show you quickly what we would have. Okay, so I hope you had the opportunity to think about that for just a couple of minutes, and it's not too complicated, but maybe you'll like this approach a little bit better. So let's see how it would go. Okay, so we have the integral from negative infinity to infinity of f of tau times u of tau times u of t minus tau, and this time we're going to think about this u of t minus tau term first. Now, as we said in class today, as long as tau is less than t, then this is equal to 1. But as soon as tau exceeds t, then this term goes to 0. And of course, if this term is 0, then the whole integrand is 0. And so therefore, we have no more contribution to the integral. So we see immediately from that discussion that we can take this u of t minus tau term out and make the upper limit t. So that we now have integral from negative infinity to t of f of tau, u of tau d tau. Now, if you think about that for a moment, you may not even have to write this stuff below. You can just think about it like this. Well, u of tau is only going to be non-zero for positive values of tau. But there will never be any positive values of tau if t, which is the upper limit of the integral, is a negative number. So immediately we can see that if t is a negative number, this is just going to get 0. On the other hand, if t is greater than 0, then again, u of tau is 0 over the entire negative part of the range where tau is negative, and this only begins to contribute when tau reaches 0. And then for tau between 0 and t, then we do have contribution to the integral. So you can think about it that way, or which is written down here, but you can almost do it in your head, I think. But either way, you conclude then that the integral, this original integral, can be written like this, which is, of course, exactly what we had before. So it's just, basically, well, obviously we come up with the same result, but it's a slightly different thought process in evaluating it in this second way. So I just wanted to make a brief remark about that for you to think about it and see which way you like better. But that's it for this brief remark, and we will still have a lecture 10 video coming soon. So thanks.